In this example, we will consider sinusoidal signal, namely cosine of t. But before that, we need to take a look at the frequency shifting property of Fourier transform. We will see that using this property, it's easy to derive Fourier transform of sinusoidal signal. Okay, well, what is the frequency shifting property? Assume that we are given a Fourier transform of x of t as capital X of omega, and if we multiply time domain function x of t by e to the power j omega 0 t, the Fourier transform of this guy is this modified signal is the x of omega minus omega 0. In other words, multiplying x by e to the power j omega 0 t in time domain corresponds to frequency shifting of the Fourier transform of original x of omega by amount of omega 0. Proof of this property can be easily done using the Fourier transform definition. For this, let this modified signal xt e to the power j omega 0 t is defined as y of t, and y of omega is by writing the Fourier integral. We have this guy here, and combining the exponential terms here, we get the Fourier transform of y of omega as integral from minus infinity to plus infinity x of t e to the power j omega minus omega 0 t dt. So the whole integral is nothing but the frequency shifted Fourier transform of x, that is x of omega minus omega 0. Now let x be a cosine signal, that is cosine omega 0 t. This signal is plotted as a time function as given in this figure, and it is even symmetric signal with respect to y-axis. And to derive the derive the Fourier transform of this cosine signal, straightforward integration method fails because cosine of t is not absolutely integrable from minus infinity to plus infinity. However, we can still obtain its Fourier transform by Euler expression. Remember, the Euler expression of cosine omega 0 t is given by this guy, which is 1/2 e to the power j omega 0 t plus 1/2 e to the power minus j omega 0 t. Okay, well, this sounds familiar, but now how? Do not worry, we know that Fourier transform of 1 is 2 pi times Dirac omega, and multiplying 1 by e to the power j omega 0 t in time domain means the frequency shifting of 2 pi Dirac omega by amount of omega 0. So the Fourier transform of e to the power j omega 0 t is 2 pi Dirac omega minus omega 0. So making use of this result and applying this for the first term in the Euler expression of cosine, for the first term we get the Fourier transform as 1/2 2 pi Dirac omega minus omega 0. Similarly, for the second term, instead of omega minus omega 0, we get Dirac omega plus omega 0. And cancelling the common terms, 2's, we get the Fourier transform of cosine omega 0 t as the sum of two Diracs, that is shifted by positive amount of omega 0 and negative amount of omega 0, and the magnitudes of these Diracs are pi. Plotting this Fourier transform, we get two Diracs located at omega 0 and minus omega 0, and the magnitudes of these Diracs are pi in the omega domain. So well, as an exercise, I leave it to the reader of these slides to show the Fourier transform of x of t sine omega 0 t as given by x of omega minus pi j Dirac omega minus omega 0 plus pi j Dirac omega plus omega 0. Here we notice that the Fourier transform of cosine omega 0 is real valued because, as given in the previous example, the cosine signal is even symmetric and the Fourier transform is real valued. On the other hand, sine omega 0 t is odd symmetric signal and the Fourier transform is not real valued. So as an exercise, please also plot the magnitude and phase spectrum of x of omega. In the magnitude spectrum of cosine omega 0 t, since the Fourier transform is real valued, magnitude spectrum is directly Fourier transform.